Right, welcome to week 2, and our topic this week is science investigations and the scientific model. So by this stage, hopefully, most of you have had a good chance to have a look at assessment task number 1, and the whole concept of misconceptions, and perhaps even had a look at some of the resources I've posted there for you under the Q&A forums for your consideration and thought. So looking at this one, we're going to get going initially. If we look at the centre of this particular screen, we can see here that we have a mental model here, which is a representation, which again is a key focus in this week's work. We've got here a replication of the student's journey, and we are elaborating that journey by way of the 5 E's model: evaluate, engage, as you can see, engage the start, explain, okay, right through to elaborate, evaluate, and of course we've got the whole exploration stage here. And in here, of course, we've got the old mental model where the student begins, and we talk here about helping the student to deconstruct their existing framework. Here we've got the teacher working in a range of roles here. In last week's session I talked about the sage on the stage, the meddler in the middle, the guide on the side, and the aim here is to address the disequilibrium, because when we have an old mental model and we have a new concept, and the new knowledge doesn't actually reconcile with the old knowledge, we're going through a transformative stage. And what we're seeing is the green, the productivity of the new understanding developing, while the teacher is helping the student deal with the frustration and the emotional connection, if you like, or even the cultural connection from stepping outside their existing framework. Ultimately, we get then to elaborate that in new understandings, and ultimately develop a new mental model which helps us to apply that to a new world context and situation. Now, what I've got here is a couple of examples from the Science by Doing website here of the sorts of investigations and the sorts of mental models that a student may bring to a particular problem. Now, this first example here on the left-hand side of the screen looks at cakes. What causes a cake to rise? And again, one sugar representation talks about sugar. One student, here is their concept. The second one has more flour. Okay, flour with the self-raising component. Obviously, there's a little bit of a half-truth going on here. Milk, not quite sure where this guy's coming from. Obviously he likes his milk. And the oven is very hot. Temperature is a factor. So again, we've got the conditions here that are pretty ripe for a really, really interesting investigation. Down here we've got a different one. We're looking at seeds. And they're talking about growing them if we put them in a dark cupboard. This person says they won't start to grow. So we've got, again, a range of different mental models operating here. What the inquiry model does is attempt to explode these through processes of exploration, through peer and scientific processes, and then ultimately arrive at a new mental model which may enable all of the learners to fit these concepts into a new framework. And another one over here looking at forces in one of the science understandings. The tennis ball will bounce more if it's hit harder, it will bounce more if the weather is hot, the tennis ball will bounce more if it's cold, and it will bounce more. It depends on the material it's made from. So we've got a range of perspective, a range of mental model going on here. This could be any topic, this could be any group of students, and this could be any science classroom. So what are we going to talk about today? We're going to give a little bit in this content lecture, a little bit of a need to understand why we use scientific investigations. I mean, are we simply paying an apprentice model to a long history of science and positivism, or is there some educational imperative behind actually adopting investigation as an inquiry approach and a knowledge building approach? So if we look at this, we can see scientific thinking and inquiry are critical to science education, and of course they are. This, it's a fait accompli, really. It's an assumption in this course. This week we're going to look at scientific investigative processes that can be used in the classroom, in addition to fair tests, as well as the importance of language. And it's this whole linguistic framing of mental models and the reinforcement and the engagement that makes these models, first of all, so powerful, secondly, so reliable to learners, and thirdly, so malleable by teachers. We can manipulate these. So diagram 1 on the left-hand side, it's learning. It's how we actively adapt and interact through learning. And this is not an elaborate model. We could go into many, many more levels and details, but really it's a very simple model. We have the real world, we have information feedback through stimuli, and then we have decision. We see a big monster. Do we run? Okay, it's a predator. Information feedback says panic, flight. The decision is to run for the hills. Now, learning, what we need to identify as educators, learning is actually a back loop process. We haven't learned things in advance. We learn it in a back loop process. And that means we go back to our existing schema and frameworks. So it's information feedback. We're going back to our existing schema of knowledge. And this can take place in what we call a single, in the middle here, or a double loop model. Now, I'm referring here to the work of Chris Agiris, who started publishing really around about the early 90s, and then joined the business world around about the year 2000 and made himself a whole lot of money. But he began as an educator. And he basically says, all right, we've got our first model here, and here's what most of us do. We have a real world, we make a decision, and on that decision we create a mental model. Every time I see a dinosaur, I'm going to run. Okay? And the mental model is formed as a result of certain single loop rules. So we see a dinosaur. Is it big? Does it have teeth? Does it look ferocious? Does it have scales? Is it running towards me? Okay, they're my 4 rules. Then I better run. So it implements my decision to run. That's what we call single loop learning. And for most of us, we can see the origins of a whole lot of social phenomena here. Racism, for instance. We can have a look, for instance, sexism, bullying. A whole range of human behaviours take root in this single loop model. Now, what does the marketing world teach us? It teaches us that we have to access not only just the single loop model, because that's impulse. Okay, people will keep doing the same things, they will never change. In order to change behaviour, we actually have to change attitudes, and the only way we can change attitudes is by linking into existing mental models. This is what Agiris called double loop learning. We can see the single loop going on here. But what we do is down here in this second loop, we actually try to integrate what Vygotsky called the ZPD. We actually try to get inside the mental model by unpacking it, repacking it, and then rebuilding it and establishing new decision-making rules so that the learner can go ahead and engage in a broader, more elaborated world. Now, we use double loop learning when we want to change a mental model. And we need to change a decision that mental model depends upon. So how do we affect people's racist behaviours? We affect the rules that underlie those behaviours. How do we do that? We actually get back to the point where we start to unpack what their model of behaviour is. Then we start to question it, and then we can start to restructure it. So these are the principles of adult learning, the principles of investigation that have been moved from andragogy, that's the science of adult teaching, versus down to pedagogy, which is the science of adolescent learning, if you like, for want of a better description. Let's go on. Single loop learning, just to summarise, it's mental models, and they affect how we work with the information and determine the final decisions we make. The decision itself changes, but the mental model will always remain the same. Okay, is the dinosaur big? Oh, it's furry. Oh, it's smiling. It's a Disney saw. Okay, I'm not going to run. But it hasn't changed the model I used to make those decisions going forward. It's the same predominant model of learning because it's very convenient, and once we've established it, it's there. It's quick, and therefore it's constantly reinforced. So we can get to the stage where it's very unconscious learning. We accept it as a truth when in fact all it is an illusion. Double loop learning takes us to a different level. Now, it's rooted in the work of Chris Agiris, and it's also got a lot to do with coherence theory. Now, I've got a diagram down here below, and I'll talk about that in a second, but it's used when necessary to change a mental model on which a decision depends. Unlike the single loops, this model includes a shift in understanding from simple and static, something simple and static, to something broader, more dynamic, and possibly more interrelated. So we can see here a mental representation. It's got 3 stages. The pre-verbal stage, the prepositional representation. It's language. Imagine an elephant. I want you to think about an elephant. Now, go back to a situation where you were a child. You'd never seen an elephant, but your mother told you about the elephant. So you had a language view of it. A natural language view of what that concept was. Then one day you actually managed to see an elephant, a picture of an elephant. You may be watching a David Attenborough show as a small child. Now you have an image of that particular elephant. Now, between the words and the image exists the actual mental model that you will form, because you will do a lot of things. You will imbue it, for instance, with images, with characteristics, with contexts, with flavours, with rituals, with a whole lot of qualities it doesn't actually possess. And they will become part of your mental model. Like, think of puppy and everyone thinks cute. Okay? Pretty unusual. Not really. It's a mental model. It's a common one. And pre-propositional representations, they're non-analogic, they're non-iconic. They can be digital and discrete, and they're arbitrary, so they've got no reference. It's really just the language. And over here, mental imagery are very fixed. They're analog, they're iconic, they're continuous, and they're isomorphic. So they actually link to something concrete, something that does exist, and something that's embedded. Now, the power of mental models is what I'd like to talk about here, and I'll just use my pointer options, and I will pick up a highlighter, and I'll just say a representation is so powerful because it's linked to our mental models through procedural semantics. Now, I know you all know the work of Ludwig Wittgenstein from 1922, his most seminal piece, where he did the picture-based theory of language. We all know what a word means because we can picture it. Words are also mental models, and his theory fits very, very nicely in the work we're doing this week and with science inquiries. So what are our learning outcomes? Describe, plan and conduct a scientific investigation of your own. Now that really is just to answer the concept of, do you really understand the whole concept of the inquiry process? I'm sure you do. We do it every day. Imagine a scenario. It's Monday morning again. I got up and I can't find my mobile phone. I've got a problem. Once I get my mobile phone, I've then got to make some observations. Okay, where did I last have it? Okay, I had it in my blue jeans, which are slung over the back of the chair in the kitchen because I got to bed late last night. So I go there. First of all, I do my investigation. Okay, what happens? Oh, it doesn't turn out. I form a hypothesis. My phone is in my blue jeans. I go and do my investigation. Fail. Okay, my thesis is not proven. I then go back and I rethink my problem. I recontextualize it. Oh, wait a minute. Maybe I put it in my jacket pocket because I'm basically a cautious guy. I don't want to put it in my hip pocket. If my jacket is hanging in my wardrobe, I form a second hypothesis. I then do an investigation. I go along, I look at my jacket, I make observations, I fumble around. There it is. Aha, I do an investigation, and my hypothesis is this is looking good. My phone is going to be here, and I reach into the pocket, and voila, there is my mobile phone. My hypothesis is proven. I go back, and the final stage of all of this, I'm so happy about it, is that I text the entire physical and chemical science class, telling you all that I've found my mobile phone. So I've disseminated my results. The scientific method, we do it all the time. It's nothing new. It should be nothing complicated for us. So our key terms this week, mental models. The way we think is embedded in the language in which we use to explain our observations. Language creates reality. Scientific literacy, again, is another component we're looking at, being able to make informed decisions. And finally, investigations. What are they? Okay, creative thinking, making predictions, planning and getting evidence, and interpreting and reporting on that evidence by way of dissemination. A lot like my mobile phone. So the scientific method. Last week I did an approach using Science by Doing, which was primarily a secondary education resource, although it can be very easily backloaded into primary and early childhood teaching, because it gives you the tools really to dissect anything. But this week I thought we'd talk about an early childhood approach. So when we talk about the scientific method, let's get onto the scientific method page and just work out what it is that we actually mean when we talk about the scientific method. And let's have a look at the mysteries of life with Tim and Moby. This is Moby, by the way.
Dear Tim and Moby, I'm watering my plant all the time and its leaves are still turning brown. What's going wrong? From Ben. Well, you could just look up the plant gardening book, but this is a really great opportunity to talk about scientific methods. Often, when people are trying to understand the world around them, they come across a problem they just don't know the answer to. This is where the step-by-step methods of scientific problem-solving come into play. Looks like Moby's having the same problem with his plant. The first step in scientific problem-solving is to recognize the problem. Right. The plant is dying even though it's getting water every day. Why? To solve this problem, we first need to understand what we already know. Okay, plants need water. What kind of plant is that? Fig tree, right. Now we need to make some observations about the plant. The leaves are brown and falling off, and the soil is wet and squishy. Next, we make an inference. An inference is a conclusion about our observations. From what we've observed, we could infer that Moby is watering his plant too much. Now we translate our inference into a hypothesis. Well, a hypothesis is any statement we can test with an experiment. What about fig plants should only be watered once a week? Well, sure, it's just a guess, but after our observations, at least it's an educated guess. We'll need to come up with an experiment to test this hypothesis. Here's the plan. We've got 3 healthy fig plants marked A, B, and C. They have the same type of pot, the same soil, and they're getting the same amount of sunlight, so the only variable is the amount of water they'll be getting. Plant A will not be watered at all. Plant B will be watered every day. And Plant C will be watered once a week. We'll check back in a month to see what's happened. Well, you know, it's been a month and I'm still wearing the same shirt. Let's record some new observations. Plant A doesn't look too good. B doesn't look so hot either. Whoa there, Plant C is doing alright. Time to analyze our data. Based on this experiment and our observations, it looks like the fig plant did best when it was only watered once a week. From that, we can conclude that fig plants grow best when they're watered once a week. Now we get to tell other people about our results and spread the word that fig plants only need watering once a week. Well, yeah, to be really sure, we should repeat this experiment several times, just to rule out accidents and variables that we may have forgotten to consider. But you get the point. Using scientific methods can help you be right more often, and not just in science class. You just have to make sure you do all the steps. If you form a hypothesis without making any observations, then you really are just guessing. And you'll never know if your hypothesis is true or not without testing it with an experiment.
Right, as we can see from Ben and Moby, it's a fairly straightforward process. Now, bear in mind it's not linear, okay, because as I demonstrated with my mobile phone example, you can get it wrong, and you may need to go back to another stage where you're undertaking another observation and inquiry. So, and what's more, even Ben and Moby were quite good there in pointing out that really replication is a key part of scientific fact. If you do the experiment and someone else can replicate it, and you can replicate the results consistently, then perhaps your hypothesis is being proven true until Popper says it's no longer true. It's falsifiable. So let's move on and have a look at another aspect here that I'd like to get on. We don't want to get too confused with the inquiry method as being purely about the 5 E's. So here's a little example we've thrown in from the POE model. Now POE's got 8 steps. Okay, so it's really about predict, observe and explain. Now the 5 steps involved here that Moby and Ben have actually identified, and sometimes they're broken into 6, but we make an observation. Okay, the first point we really start with a problem, and then we make an observation. We form a question, okay, and from that question we then are able to deduct a hypothesis. The hypothesis leads us to an experimental framework where we can actually test the hypothesis, and again the key words here are fair test, and we'll get onto that in a minute. And then we'll analyse and draw a conclusion, and the final part of that of course is disseminating the good news. That's what science is, it's good news. So a little example of the POE model done by a student at a school. The hypothesis for a project at junior school about the younger years was having a small carbon footprint, which means that kids at junior school produce less carbon when travelling to and from school. That was largely the hypothesis. The observation was this person noticed that there were about 3 times as many students were arriving by car than bus. Okay, which led to the formation of a research question, which they found that this whole school produces 505 tonnes of carbon per year, and that 3 times more people went to school by car than by bus. And the age goes up as carbon emissions actually go down. So the older and more independent students get, the less times they drive with mum and dad to the car and then to school. The fact that age goes up and carbon emissions goes down disproved the students' original hypothesis. Okay, so the aim was that young students have smaller carbon footprints, again, and let's pick that up here, and therefore they produce less carbon when travelling to and from school. Ultimately, through a process of predict, observe and explain, okay, the hypothesis was ultimately disproved. A little example there of science in action. The concept of fair test, this is a Keith Patterson video, and I'll just try and actually... We'll have a look at this Keith Patterson video here, and it really introduces the concept of a fair test.
I'm sure most of us have enjoyed playing with baking soda and vinegar and watching the chemical reaction that takes place. But as much fun as it is, this isn't really a science investigation. A science investigation begins when we have a question we'd like to know the answer to. We use observations and experiments to help us find the answer. So today, I'd like to take this simple home experiment one step further. I have 3 different types of vinegar, and I'd like to ask the question, which type of vinegar produces the biggest reaction with baking soda?
Right, we can see there that it is pretty much going beyond the notion of an experiment, looking more at what is in fact an investigation. Okay, so it's really important to to pay mind to that particular difference, which is quite significant. Now, our demonstrator goes on.
To do this, I need to make sure that I have the exact same amount of baking soda each time I do the experiment. So I'm going to use a level teaspoon because that's a measurement that's quite easy to be accurate with. It's just as important to measure the amount of vinegar that I'm using. In this experiment, the only thing that I want to be different is the type of vinegar that I'm using. So everything else needs to be exactly the same.
Right, and a really interesting notion here. What she's subtly doing here is introducing the notion of independent and dependent variables. So she's working out what she wants to keep the same, what she's going to allow to vary or test, okay, and therefore how she's going to actually measure the differences therein. So, it's really quite a nice little example of, a science investigation that covers the principles of fair test, and again, by, manipulation of variables in a way that's going to produce a reliable and generalizable result. That's what happened next.
I have a pen ready to make a mark on the glass so that I can measure how high the bubbles go. There's no point doing a really good experiment if I can't make a really good observation. Okay, now it's time to pour the vinegar into the baking soda and observe what happens. It's fizzing quite fine and it's made it about that far up the glass, so a bit over halfway. Now it's time to try with the red wine vinegar and see if the reaction is any different. Oh, so it's gone a little bit higher than the white vinegar. And finally, I'm going to try it with the balsamic vinegar. Right, so that is clearly a much more vigorous reaction than both of our other vinegars. It's gone all the way to the top of the glass. So it seems as if balsamic vinegar gives the biggest reaction with baking soda out of my 3 vinegars. But at the moment, that's just my theory. It's my hypothesis that balsamic vinegar produces the biggest reaction with baking soda.
Now, how is she going to actually test that hypothesis? Under the principles of fair test, clearly there's another step involved.
But just because I have this idea or theory, it doesn't necessarily mean it's true. For my results to be reliable, I need to make sure that what just happened here is more than a chance event. So to make sure my results are reliable, I'm going to do the experiment again and again. I did the whole experiment 2 more times. Each time I was able to make more measurements and add evidence to support my hypothesis. With 3 trials completed for each type of vinegar, I calculated an average for each, so that it was easier to make sense of all the numbers. Putting these numbers into a graph with a title and clear labels means that my results start to make a whole lot more sense. A graph gives us a really clear image of how the different types of vinegar compare. Because I did a fair test, I know that I've come up with a really good conclusion, that balsamic vinegar is the most reactive with baking soda. I know this because everything in my experiment I kept exactly the same except for changing the different type of vinegar I used. I also repeated the test 3 times so that I knew that my results could be trusted. So, I've answered my question. Balsamic vinegar is the most reactive type of vinegar when mixed with baking soda.
Right, so a really nice little example there, I think, of how to actually go about employing the scientific method, and particularly putting emphasis on the fair test component. So, as a teacher, how do you do this? I mean, do you have to commit this to memory, or are there resources and approaches out there that are going to help you and able to embed this and do this really as a second thought process? So let's have a look. Oh, look, another one I threw in here. Actually, I'd forgotten about this one. Is making and launching a Coke bottle rocket. I threw this one in because I really, really like this one myself. And it can also be done with racing cars. You can make a Coke bottle, get each student to bring in a Coke bottle, and they can design their own racing car, which basically means usually the use of tape and glue and a frame, and a frame and some wheels. Basically, Lego wheels are often good. And what they do is they actually attach the bottle to the wheels, and they can actually convert a Coke bottle into a really little simple drag bottle. Drag racing car, and all they need to do is have some of the substance in the car and insert about 5 little Mentos, the mints, and stand back and watch how fast and how far the car actually runs. It's quite rocket powered. But here's a little example. Let's have a look at this one. This is using air and empty Coke bottles. Great little science experiment. Now, of course, there's a lot you could do with that one, isn't there? Think about hypothesizing about rocket design, a whole range of aspects you could throw in there in terms of getting the students to design their own rockets and which is the most flyable. It can go a little bit further too with the drag carts because you can actually play a little bidding game. In your science class, you may award science credits to each different group. The group can then use those credits to bid for instance, their favourite soft drink, and they can use their soft drink as a fuel to actually drive their super-powered little soft drink motor vehicle. A lot of fun can be had with this kind of learning. It can involve interaction, it can involve collaboration, it can involve a little bit of game playing, a little bit of competition, and in the end it can lead to an awful lot of learning. So how do we capture this as a teacher? Let's have a look. First of all, let's go back to the ACS. Now, the ACS has 3 distinct strands, and now a lot of people are thinking, as you're looking at your assessment task number 1, for instance, this is why I've thrown this in here, and I must thank Marnie Hughes for prompting this, but the ACS has got 3 distinct strands, and we often get preoccupied with the content strand. And this is the message to you as primary teachers: don't get preoccupied with content. The other 2 strands, the science inquiry strands and the science as human endeavour, are just as important as the content. And often we focus on the science understandings, biology, earth, space, science and physical sciences, without really turning our mind equally to the science inquiry and the science as human endeavour strands. Now, for your purposes, don't worry about finding too much ACS evidence in the sciences for this. It's great if you can bed your project down, whether it's biological, earth, space, science or physical, what you're focusing on for assessment task 1. But bear in mind, it is well and truly embedded in the inquiry strand. And you can see here, for instance, the principles of the inquiry. The 6 principles are there: the use and influence of science, the practice of questioning and predicting, planning and conducting, processing and analysing data, evaluating, and finally communicating. So when you're looking at assessment task 1 and you've got to make explicit links to the ACS, by all means look at your science understandings, but also look closely at your science inquiry content descriptors and also your science as human endeavour descriptors, because they too will give you a wealth of information in which to locate your particular project. Okay, so let's have a look here. Now, the Science by Doing website, and I'll provide these resources, I'll put them together for you and package it for you on the Q&A forum. And what it is, it basically teaches you and provides you as a science teacher with a model for conducting investigations. So when we look at it, it begins with things that could affect my investigation, and this is what you're encouraging your students to think. Think as scientists in their own world, as Piaget would have said. What is going to affect my investigation, and what things do I have to measure and observe to really think about whether my investigation is going to deliver any real knowledge? What variables do I choose? What am I going to measure? And what will I not change? What am I going to keep constant? So here we're starting to decide between the dependent and the independent variables. So what things are you not going to measure and why? And the nice thing about the investigation planner offered by Science by Doing is that it's a downloadable PDF or Word file. What it does, it allows you to manipulate it for your own science experiment, and it enables you to get your students to move through those thinking processes. What will affect my investigation? What do I need to measure? Things I will change, things I will measure. I will not change and I will not measure. The next phase, obviously, is making a testable question. My testable question is, when I change this, what will happen to that? When I change the independent variable, what happens to my dependent variable? Okay? When this testable question gets put into a statement, it becomes an hypothesis. When this changes, it would lead to this kind of change in that. When children are young, they will have a smaller carbon footprint. If we go back to our POE example. Data collection. First of all, we go to procedure, my apologies. Exactly what will you do? Write down the steps, use dot points and numbers that you follow in order like a step-by-step recipe. And again, this is all done as a group. Students do it collaboratively so that everybody comes along. As they say in America, no child is left untouched or unstoned, as some people cynically say. Include detailed and labelled drawings if you wish, and what materials do you need? What safety precautions are you going to have to honour? And finally, data collection. What will I change? What will I measure? How will I record this data? And the number of times I'm going to carry out this investigation. Now, this is a pro forma. And by pro forma, I mean it's a model set up by the Science by Doing people, so that every child in your class can have it, every group will have it, and they will be working through a series of steps. Now, why is that such a good thing? Because you as a teacher can actually go back and check their process, because the assessment of science is as much about the assessment of process as it is content, and we'll come to that in a minute. But you need to be able to walk around a group as the meddler in the middle, and you need to know the steps that each student and each group is working at, so that you can actually dialogue with them about that. You can walk up and peer over a group's shoulder and say, okay, what's your testable question? Oh, they don't know, they're unsure. Go back a step. You know where to jump in. And soon before long, this becomes like second nature to you. It becomes your effective teaching, your facilitation model. You can be the sage on the stage at the front, you get the groups going, you can be the meddler in the middle, and then ultimately, when they get down to this stage here, what are they going to do? Some groups may get stuck. You can be the guide on the side, working closely between and beside each of those groups. Some data capture. The Science by Doing people don't leave you just with the method. They actually give you in their little document and workbook examples ways of recording. You can see up here on the left-hand side a sample table. What I changed, the independent variable. What I measured, trial 1, trial 2, trial 3. And that gives us some indicator into the replicability of your actual science experiment. You can then graph the results. What was your dependent variable? What was your independent variable? And what happened each time you conducted that experiment? Ultimately, we come over here to finding patterns in the results. When I changed X, what happened to Y? When I changed X, what happened to Y? And just to give you a linguistic example of how powerful mental models are, here's a little example that comes out of the field of linguistics. Think of this particular statement. The X was crying, so the Y picked it up. Now, in this case, what was the X? You're probably thinking baby. When you're thinking in this case, what was the Y? You're probably thinking mother. Now, that gives you an indication of the power of mental models. A totally random concept, it could have been what the X was crying, it could have been baby still, and the Y picked it up, the dingo, it could be a really strange invariation. And it's really important to, think about the power of mental models, and this is why we're doing this. So we're trying to embed a new mental model. When I changed X, this is what happened to Y. Now, the next thing I want to know, extension. What was my conclusion? Did it support my original testable hypothesis? Okay, what next? What's the step beyond this? What else would I like to know and change? And here is your extension work as a teacher. Once the thesis has been proven or disproven, if it's been disproven, they go back and they restart again. If it's been proven, the next thing they do is they identify where they want to take that knowledge at its next phase. We come to assessing content and process. And in your Science by Doing open investigation resource, I'm putting up on your Q&A session in the Moodle, you will see that there is this rubric. And this rubric goes through the 6 stages of inquiry-based investigations. And for each of those stages, it ranks the learner's level of performance at beginning, developing, competent, accomplished, or exemplary. Now it does this because we need to assess the process as much as the content. Okay, that's what we're working on here, building a process approach to science, an inquiry-based approach to science that's going to support a student through a lifetime learning journey. And we can see that it poses appropriate question, identifies relevant variables, follows a scientific procedure or a procedure of some kind, observes and records relevant data, organises and presents results, and is able to draw conclusions and explain the science of the conclusions. So it's one thing to say that baking soda creates an eruption, okay, when we add vinegar to it. It's another thing to go back to the chemical science and actually say what's going on there. Why is that happening in the way that it's happening? Okay, so our next point and final point. Again, these are available to you as a resource to help guide your teaching and also guide your teaching for Assessment Task 1 when you're looking at misconceptions. They're available for a resource for you in the Q&A section. So the Zoom session this Wednesday. And we are going to actually look at a couple of set things this Wednesday as we go through. We're going to revise the whole notion of scientific investigations. Now, in this week's learning tasks, you've got 6 explicit learning tasks that take you through the notion of doing some minor investigations of your own. If you can't get access to the resources to do those investigations, or if it's just one of those weeks and you know you're not going to get round to it, then have a look at some of the ones I've put online here. The little plant one with Ben and Moby is a really simple one. It's an investigation. The second one with the 3 different types of vinegar is again another science investigation. Failing that, you can Google many. So if you can't complete the science investigations yourself, then use some of the videos as a means for completing tasks 1 through to task 6, okay, in this week's tutorials and online work sessions. You'll also find in there as a guide to the Australian Curriculum in Science, which takes you through the 3 strands, the science understandings, the science inquiry skills, and also the 3rd strand there is the science as a human endeavour. So you've got your 3 strands there. The ACS takes you back, there's a link to take you back there and actually help you recall what those strands are and how important they are. We'll also look at the importance of language. You know, the X was crying, so the Y picked it up. Mental models, our whole concept of meaning, very powerful stuff. Okay, and it's the basis. Here is where we go in with our learning theories and we try to disrupt mental models that are causing misconceptions. And this brings us to the first assessment task, point number 4. Devising a diagnostic tool to use questioning to make comparisons to the language used by learners in order to establish misconceptions. We were talking about Vygotsky, the ZPD, the more competent other, as a way of shifting, as a metaphor for shifting learner orientations. And the second part of task 1 is to create a learning sequence that can be used to correct the misconception. So in other words, you're going to need to devise a scientific investigation, the very stuff that we're talking about this week. So again, once you pick your science understanding and you embed it in your science inquiry tasks, you are going to need to devise, under point number 5, the second part of task 1, a learning sequence that you can implement to correct a misconception. It's quite a challenging task. And again, to pick up on a topic raised in the Q&A in week 1, you are not confined purely to the chemical and physical sciences for this inquiry task, for this assessment task. You are able to choose from all of the science understandings because the focus of this task is on science inquiry skills and also science as a human endeavour. They're the 2 areas, the 2 strands in which this assessment task number 1 is heavily embedded. Alright, thank you, and hopefully I will see you online at our Zoom session on Wednesday at 10 o'clock.